So let's see what that value is. 12.169 divided by 1.832. Okay, so that's going to be negative 6.64 is
Okay.
the x-intercept, right? Which we have to substitute into there. So the Km is equal to minus 1 over minus 6.64, right? Is equal to 0.15. Okay?
Okay.
All right, and it's a km, which is a unit of concentration,
Mm-hmm.
right? It would have been millimolar,
Right.
right? Millimolar.
Okay.
So there's your calculated Vmax, and
KM tells us half the Vmax.
so it tells us the concentration that gets us to half the Vmax. Okay, so we thought that the Vmax might be about 0.09, so half of that is about 0.045, which is about that number there,
Uh-huh.
right? And so then the corresponding concentration is 0.25, and 0.15 isn't that far from that,
Okay.
right?
Okay.
Does that make sense?
Yeah.
Yeah.
Thank you.
Yeah. Yeah, so it's really being able to work with these equations and derive the Vmax and
Okay.
the Km.
I can do that.
Yeah.
Thank
Now,
you.
it's the most straightforward thing is
Mhm.
this scenario where we have, maybe millimolar units here
Mhm.
and micromoles of product per minute here.
Okay.
And there's no exponent.
Right.
Okay, because when we then transform it and get these numbers, right?
Mhm.
Get this line, get this equation, right? We don't have to worry about doing any adjustments because of exponents,
Okay.
okay? Does that make sense?
Yes.
Okay, now, let's say you have this scenario. We do the Michaelis-Menten rate curve, which is like this, okay? And these units here are the substrate concentration, just plain old millimolar,
Mhm.
okay? And then these are, this is the initial velocity, okay? And it's micromoles, or let's see, I'm gonna change it a little bit. I'm gonna say moles per liter per minute times 10 to the fifth.
Okay.
Okay, right? And so let's say this is a 1, this is a 2, and this is a 3. And this
Not
is
times 10 to the negative fifth, or it's minus 50 points.
Well, it's as long as I've labeled that correctly, right? Right? And this is correctly labeled, right?
Okay.
Okay, so what's the estimated Vmax there?
About 5?
Okay, 5. But that's not the true value, right? The true value, so this 5 is really the moles per liter times 10 to the fifth,
Okay.
right?
Mhm.
So what I have to do is take that and divide it by 10 to the fifth to get the true moles per liter per minute.
Okay.
Because this label is saying that 5 is the true value times 10 to the fifth.
Okay.
Okay.
So, but
So
if
this
we,
is 5 times 10 to the minus fifth. Moles per liter per minute.
okay.
Do you see what I'm saying?
But if we did, you can't just take 5 and do times 10 to the negative fifth. That's incorrect.
Yeah, you could.
Oh, okay.
Right?
Okay.
Right? I mean,
Yeah.
I'm showing you that to get this, since this is this times this, To get this,
Mhm.
we have to take this divided by this.
Okay, so
Right.
this initially, this number represents 5.
This number, this
Alone.
5, is equal to whatever the true value, the true moles per liter per minute times 10 to the 5th.
Okay.
So to get the true moles per liter to
Moles per
minute,
liter per
we have to
minute.
take 5 divided by 10 to the 5th, right? I'm dividing both sides by 10 to the 5th.
Right, that makes sense.
Right?
Okay, that makes sense.
Yeah.
Thank you.
Okay, so if this graph has that exponent
Mhm.
adjustment, this one's gonna require it, right?
Mhm.
Because the line, right, is going to be basically using those numbers, right? Right, so what,
Mhm.
so you say B is equal to 1 over the V max, right? So the V max is equal to 1 over B, right? You get whatever that number is,
Uh-huh.
right? This will give you some value of Z, right? But you're going to have to divide it by 10 to the 5th to get the true value.
Okay,
Mm.
so we can still
Right.
find all these values the same way and treat
Mhm.
it the same,
Mhm.
and then just switch your units
Yeah,
after you've done all of that.
that's exactly what you
Okay.
would, that's what I would
Okay.
do.
Okay.
But the key is, this number, whatever you get, should be pretty close to your estimate,
Okay.
right?
Mm-hmm.
And you saw what we did,
Yeah.
right? Right? You can always go to the raw data too,
Mhm.
and make sure that it's consistent with the raw data.
Okay.
So if we estimate a value, right,
Mm-hmm.
and we have to do some little manipulation to it,
Mhm.
we should be able to go back to the raw data and say, is it close to what I would expect it to be?
Right.
Do you see what I'm saying?
Mm-hmm.
Mhm.
That makes sense. Okay. Thank you.
Yeah, you're welcome.
You're welcome. Do we need to bring laptops to that, or are we generating
I won't,
graphs?
you know, it would, no.
Okay.
I'll generate graphs for you.
Okay,
Yeah.
thank you.
You'll need to know how to interpret them
Okay.
and how to work with the equations that you get from them.
Mhm.
Mhm.
Okay, thank you. Can I take a picture?
You can have it.
Oh, great, thank you.
That second page. There's that first page.
And I have one more question, but if you wanna ask questions.
No, you go ahead. You don't
Okay.
mind if I'm filming?
No,
everything?
no, no,
Okay.
it's fine.
Yeah, because I think we were probably gonna have a similar conversation, weren't we?
It was
A
gonna
little
start
bit?
here, yes,
Yeah,
that's right.
yeah. Mhm.
Alright, so the next one was on, where was I? No, this one, sorry. We're talking about, okay, bed volume versus void volume
Uh-huh.
versus elution volume.
Uh-huh.
I'm kinda confused on that.
So the elution volume is whatever volume that your sample comes out in,
Okay.
right?
Mhm.
So you put your sample on the top of the column,
Mhm.
immediately you start collecting drops out of the bottom.
Uh-huh.
If your sample comes out after 2 milliliters, then 2 milliliters is its elution volume,
Oh, that makes sense.
okay?
Okay,
Yeah.
yeah.
Okay, now, the bed volume, so let's say this is our column here, right?
Mhm.
And we have these disproportionately large beads in there, right? Okay. The void volume is the volume outside of the beads. Okay?
Yes.
It's all this space in between the beads.
Okay.
So what molecules have access to only the void volume?